Welcome to everybody. Today we're dealing about the exercise of a shape beam. The scope of this video is to demonstrate the formula explained in the previous lectures and to calculate the shear flows around this shape section. Here you can see already all the geometrical data of this section, with the web indicated with the letter A in lowercase. A is equal to 300 millimeter. B is the flange. We have clearly this section is 1 times symmetrical, because if you take this axis x sim, so this is also the centroidal axis. We see here the centroid with the coordinate A over 2 and B over 4. Between a few seconds we will switch on MathCAD to see all these calculations. So x sim is the symmetrical axis and also the centroidal axis. So this section is 1 time symmetrical, because if you cut this section at 0.3 and with the rigid rotation move the upper part, so the 3, 2, 1 part on the 3, 4, 5 parts, the two parts match equally. So in this case, this is the proof that this section is 1 time symmetric. So the web of this section is the side 2, 4, that is clearly A, and the thickness of the web and of the two flanges are equal to 20 millimeter, and we have an shear load applied on the y-axis. The y-axis is this for us, y and x-axis is minus 150 kilonewton. So this load, we make the hypothesis that this load through the shear center of this section, that we must calculate the location along the x sim, that is equal also to xcg, because we know that from the theory that if a open section, because this is an open section, an open thin-walled section, if an open section or a closed section also has a one symmetrical axis, the shear center lies on this axis. But where? For some section, the shear center is located at the intersection of the web and flange, such as the T-shape. For T-shape, this is the shear center, okay? But for this type of section, the shear strand, we shall see that is located on the left side of the web, so is at a negative x location. Okay, so the shear center is also known as the point where if I apply the SY, so the load, in this case the shear load, we have no twisting of the section. So d theta over dz is equal to 0. So we have no twisting of the section. No twisting and no bending of the section, clearly. If we want to avoid twisting and bending of the section, we must apply this shear load through the shear center. But we must calculate its location. We know that the shear center lies on this axis, but where is the shear center here? We don't know at this moment. So we switch on MathCAD to see the calculus. So first of all, we have here MathCAD. This is the sheet of MathCAD. As first things that we must calculate is the section properties. And you see the dimension A, B, T and SY. You can see my cursor. This is this arrow that indicates the quantity. So A1, A2 and A3 are the area of the three rectangular shape that which is made this section. So we have this first rectangular shape, first, second, and third rectangular shape. So where you see G1, G2, and G3, this is the centroid of singular rectangular shape. First, second, and third. A1 is the first area, A2 is the second, A3 is equal clearly to A1. B times T is the simple area of the rectangular shape. And so we have the centroid xg and epsilon in yg of single J1, J2, and J3. So we have, for example, 75 millimeters, because we are referring with respect to this axis y and x. So this J1, for example, the xj1 is located to the half of b. So b half is equal clearly to 75 millimeters if b is equal to 150 millimeters, and yj1 is located to clearly yj1 is equal to a, so a is equal 300 millimeters. For the other centroid, you are able to obtain the other dimension that we see here. For G2, xg2 and yg2, and for G3, xg3 and yg3. So the centroid, or the center of gravity, also here indicated with the coordinate xcg and ycg, you know that is calculated as the sum of the relative coordinate of the centroid centroid for the height area divided by the sum of all the area of single rectangular shape, so A1, A2, and 3. So we have xcg is equal to the b over 4, because 75 millimeter is b over 2, 75 millimeter divided by 2 is b over 4, and epsilon cg is equal to 150 millimeter, that is equal to a over 2, so half a. We have this coordinate here, a over 2 and b over 4. This is the centroid of this shape. Now we must calculate the moment of inertia of this section. Clearly, in this case, we have the general relation of a generic shear flow. So we have this quantity here divided by the, we have the moment of inertia, the product of inertia, and the shear load along x and y direction. Now, if we have a one-time symmetrical section, clearly the product of inertia xy, and you can prove this, is equal to 0 millimeters at 4 power. So also Sx is equal to 0 kilonewton, because we have all the Sy. So in this from this general relation, we can put equal to 0 this quantity Ixy. So also here go away. This quantity and this quantity go away, and so Sx is equal to 0. So all this quantity here, the first member is 0, and we obtain only this quantity here. I simplify this equation in this way and obtain this relation, that is minus Sy divided by Aixx integral from 0 to s of Ty ds. So this is the general formula that we must use here. So the only moment of inertia that we must calculate is Ixx with respect xcg axis or xcm axis. And with MATCAD, so with MATCAD we have the splitted screen now. On the right side we have the general formula in this case, and now we have on the left side the MATCAD with the Ixx1, that is moment of inertia of the first rectangular shape, this one where is written G1 or the flange 1, 2, so is equal to b times t at third power divided by 12, that is the moment of inertia with respect to its own centroidal axis of this rectangular shape, plus a1, the area of this flange, times the distance of the difference at square power from the between the distance of the yj1, that is the y coordinate of centroid g1, minus the coordinate of the centroid cg along y-axis. So yj1 minus ycg at square power, all these quantity at square power, is equal to this stuff. So this is the moment of inertia of Ixx1. Ixx2 is equal only the t times a at third power divided by 12, because this web, the centroid of the web, clearly you see that is located on the same axis x sim. So this quantity here is equal to 0, because yg2 minus ycg is equal to 0. So we have only the moment of inertia of the web with respect to its own centroidal axis. So if we make some calculus, we obtain this stuff here. Now Ixx3, it's the moment of inertia of this flange, clearly is equal to Ixx1. I remember you is 1 times symmetrical, and this quantity here, the flange 1, 2, is equal clearly to flange 4, 5. The total moment of inertia Ixx is equal to 2 times Ixx1 for the reason that I explained a few milliseconds ago, plus Ixx2, and this is the moment of inertia of whole C section. Now we switch on shear flow. How can I calculate this shear flow? We see here the formula that is similar to this, but where is the integral here? Here the integral is already resolved, but now I can calculate this quantity that we see in MATCAD. So we must put a abscissa and certain abscissa around all these point 1, point 2, point 3, because here we have the x-sim. We have a certain intersection at point 3 and dummy intersection at point 4. So these abscissa is 1, S2, S3, and S4 are our reference abscissa where the shear flow is positive. So the shear flow is positive if are conquered to this direction from right to left. If the shear flow follows this direction from right to left, is positive. Also here from the S2 the shear flow is positive if we obtain a shear flow that move from 2 through 3 points, the point 3. We have another positive shear flow if the obtained shear flow in the inside 3, 4 of the web, the shear flow move from point 3 to point 4. Is a shear flow positive in the lower flange if we obtain a shear flow that moves from point 4 to point 5. So this S1, S2, S3, S4 is a certain circuit that we impose arbitrarily at start of the our exercise. This is the positive direction S1, S2, S3, S4 of our shear flows. Now we are on the top flange 1, 2. So S1 is our reference abscissa. Now we must derive a formulation for the y coordinates. So in this case we have when y1 is equal to this distance is equal to a over 2. This is a over 2. So when yy is equal to a over 2, s1 is equal to, if this is an abscissa, our reference abscissa, here is our 0 point, 1 is our 0 point of this s1, so s1 is equal to 0. When y2 is equal, y2 is the same coordinate, so 2 point is on the same line of the 1 is the number, so and so the coordinate y is equal get to a over 2, so y2 is equal a over 2. S1 is equal to our reference abscissa, and here in point 2, but point 2 we have all this quantity here, the flange, the length of the flange 1 2 is equal to length of the flange b, so s2 is equal to b. Okay, this is our reference abscissa starting from 0 and end to b. The y coordinate is constant clearly because 1 and 2 are on the same line. So we have this formula, y minus y1 divided by y2 minus y1 equal to s minus s1 divided by s2 minus s1. So clearly this formulation is equal to y minus a over 2 divided by a over 2, sorry, a over 2 minus a over 2 here, so 0 equal to s minus 0 b s2 minus s1 0, so b. So this is equal to b times y, the multiplication cross direction, so this for this and this for this, we have b times y minus b times a over 2 equals to 0. So now we have here the relation y is equal to a over 2. So if I put this equation for y in the integral here, we obtain qs is equal to minus sy over ixx integral from 0 to s1 t times a divided by 2 ds1, that is equal minus s1 ixx t times a over 2 times s1. So this is the formulation that we have here. Q12, so the splitted part is on the left. Q12 is equal to, so this is the general formulation, Q12 as a function of S1 is equal to minus Sy divided by Xx times T times A over 2 times S1. So S1 move from 0 to B. So Q12, I can evaluate this quantity S1 at 0, but S1 Q12 is equal to 0. So this is our convention and opportunely chosen abscissa, because here the shear flow at point 1 is equal to 0. But this is physically explained because on the right side of 1 we don't have nothing, no area. If we have no area, the shear flow is equal to 0, because I remember you that this quantity here, this integral is equal to first moment of the area, that is in Italian is momento statico. If the first moment of area we don't have an area, is equal clearly to 0. So in point 1 is a convenient point, because on the right side of point 1 we have no area, the shear flow is equal to 0, and from 1 to 2 we have a certain shear flow. For this reason I started from here, not for a stupid reason or for a generic reason that we don't know. So now we can calculate the shear flow at point B, that is equal this quantity. MathCAD here reported the kilogram over second at square power, that is equal to Newton over meter. If you divide this quantity for 10 at -3, we obtain a value of 3074.6 Newton per millimeter. So I can switch here the unit of measure. I write Newton divided by millimeter. We obtain so clearly 374.58 blah 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 Newton millimeter. So now I want to calculate Q23. As made for Q12, we must derive an equation for this quantity here, for this piece of the web, the part 2-3. S2 move also from 0, because here start the second hour, the hour second abscissa S2 start from point 2, from 0 to point 3, but point 3 is located at a over 2. I must derive the y equation. I derive the equation 2-3 clearly after the equation for y 3 and 4 and 4 5. You can calculate this equation y as exercise. Remember that S3 start from 0 from point 3 and goes to point 4, where the length is equal to a over 2. So this quantity here, starting from 0 to a over 2. And so this quantity here starting from 0 to a over 2. And this quantity here start S4, start from point 4. Okay, so this is 0 and this is the quantity B. So now we can derive the equation y for the 3 side. We have, when y2 is equal to, y2 is located at a over 2. The point 2 is located at a over 2. S2 starts from point 2, so clearly is equal to 0. When y3 is equal to, now y3 is equal to 0, because this is our reference axis. So yCG and xCG. So in this case, because I trace this axis, xCG and now yCG. Okay, we refer with respect this axis, not with respect the axis in orange with the orange pen, y and x, no, with respect this axis here. Okay, now we have, with respect the centroidal axis, if you want, we have that y3, the point 3 is at 0, yCG or at y equal to 0. So we have here 0, but S3 is equal, as said before, equal to a over 2. So the equation is the same. Y minus y2 now divided by y3 minus y2 equals to S minus S2 divided by S3 minus S2. That give us, so if I put this equation also in this integral, now we have here Q23 is equal to minus Sy Ixx integral from 0 to S2 of t multiplied by A2 minus S in the S1 plus, now plus what? If we are starting from point 2, at point 2 we have also the shear flow calculated with Q12, because Q12 move from 0 to B, but B is the same abscissa coordinate of the point 2. So at point 2 I have a certain shear flow. When I start again from point 2 for the from the web, in this case, I don't lost. I must don't lost this the previous shear flow that is acting in point 2. So now I must sum at this shear flow the shear flow obtained Q12 at S1 equal to B. Now I can calculate this quantity, and this is Sy divided by Xx. Q23 is equal to this quantity. That is the same that we have obtained from starting from the equation y here and put this equation in the integral. So now, if I want to calculate the shear flow of this quantity here, Q23 move to 0 S2. So if I put 0 here in this quantity here, so we see here, if Q23 with S2 equal to 0 millimeter is equal to the same thing that I said before. Now here is Newton over Newton of meter, but if you divide this quantity for 10 at -3, we obtain the same value here. So we can prove this with the magical stuff that I write here, Newton divided by millimeter, and voila, this is the magic. So same thing here. If I evaluated this shear flow at A over 2, obtaining this value, Newton divided by millimeter. So we obtain at A over 2 a shear flow equal to 561.876 Newton millimeter. So if you understand the game, you now are able to calculate by yourself the equation for the shear flow 3/4 and the equation for 3/5. Remember that this quantity now here is a negative quantity, so this is minus A over 2. But on the lower flange we have from 4 to 5 a positive quantity, because is the same of the flange 1, 2, so 0, 2 plus B. But here the point 4 with for the side 3, 4, the point 4 is located at a station Y that is located at minus A over 2. So for you now, and to reduce the duration of this video, I write only the quantity that you must use to derive the equation we have. And the equation that we have also here, 3/4, you obtain this shear flow if I put this quantity. When y3 is equal to 0, is3 is equal to 0. When y4 is equal minus A over 2, S4 is equal to A over 2, because S3 is positive if move from 3 to 4. But y is another consideration for y. Y starting from 0 to minus A over 2, because this is the reference axis YCG, XCG for the y coordinates, and for the S coordinate we must use this convention, this orientation of the abscissa S3 that is positive if move from 3 to 4, so 0 to A over 2. Now I obtain a certain y equation that if I put this equation in the general integral here, I obtain this quantity here, Q34, as a function of S3. Note that here the minus sign is replaced with plus sign because making some calculus, the sign minus is simplifying a plus sign. So, but if you make some calculus, we obtain clearly this equation. And now, for the S3 move from 0 to a over 2. If I put S3 equal to 0 millimeter, I obtain this stuff here, because if I here's this and write as the same millimeter, I obtain this. So clearly. But you must don't forget that the shear flow Q34 is equal to clearly Sy divided by Xx integral 0 to S3 Ty the S3 plus the previous shear flow. So the shear flow Q23 at S2 equal A over 2. This is for all shear flow. Also, when I calculate the shear flow at here for 5, I have the shear flow, the general formula that is this, but now we have S4 and S4 plus the previous shear flow that is Q34 at S3 equal to A divided by 2. So, if I make this calculus, I obtain a shear flow, an equation for the shear flow that is equal Sy divided by Axx times T times all these A over 2 times S5 minus A times B divided 2. Now, the lower flange, the side 4-5 moved to 0, as said at start of the video and in any part of this video. S4 start from 0 to B. So at 0 we have clearly the same shear flow that we have calculated previously for this nature of this formula, because if y is equal to 0, all these quantity disappear and we maintain all the previous shear flow. Now I made an example on the shear flow 3-4, but we can prove that clearly when S4 is equal to 0, I must obtain the shear flow at A over 2 for the shear flow Q34. So I must obtain 3.74.6 Newton millimeter. That is the same shear flow here, this shear flow. Now, clearly at the B, at value of V, as 5 equal to B, we obtain a 0 Newton over millimeter. Now we can calculate the resultant forces, as you see from MATCAD. Now, the resultant R12X is the upper flange resultant, and 45X is the lower flange resultant. So we have to integrate the shear flow Q12 as a function as 1 that we have obtained before. So this equation here must be integrated from 0 to B, that is the length of the S1, and this is equal to this force 2.8 and blah 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 times 10 at 4 power Newton. R45X is equal minus to R12X, or minus the integral of 0 to B of the shear flow Q45 as a function of S4, because now we can see this. So The obtained shear flow are all positive now. The shear flow is all positive now. That's we have obtained from MATCAD some values that we see here, also the well-known diagram of the shear flow of a C-section. We have 0 Newton millimeter here. At point 2 we have 3074.6 Newton millimeter. Now on the web we have an starting from the same value. So this is the consideration that I made before. For the upper flange I arrives to point 2 has this quantity. So when I restart from the web from point 2 we have the same value, that is 374.6 Newton over millimeter. The trend of on the web is a parabolic trend of the shear flow. When you see with the maximum value located clearly at on the xc axis or xcg axis of this our C shape, and is equal to this quantity. Now from point 3 to point 4 we return at the same value at point 2, because this section is one time symmetrical and is symmetrical with respect to this axis in green. The same in point 4 I must obtain the same value of the point 2. So at point 4 we return to 3074.6 Newton millimeter, and when I restart from point 4 for the shear flow in the lower flange for 5, I must again obtain the same value at point 4, that is 374.69 Newton millimeter, and to conclude this shear flow at 0 Newton millimeter, because here is valid the consideration that on the right side of point 5 there is no area, so the shear flow clearly must be equal to 0. So this is the general diagram of the shear flow. Now if all the shear flow you see are positive, these red arrow are the representation of our shear flow that are following the direction of S1, S2, S3, S4. If this shear flow following this direction, as said at the start of this video, these shear flow are all positive. Now we have said that the shear flow is passed through the center, shear center of this shape, but is located at E quantity from the edge to 4. Now I want to obtain the resultants R12x, R24y, and R45x. To obtain this resultant, I must integrate the shear flow as a function of S1 here, as a function of S2 here, as a function of S3 here, as a function of S4 here. So we have the abscissa reported here. And how I made on MATCAD, you see that R12x is equal clearly this integral from 0 point A to point 2, that is B. Clearly also for 4, 5 flange, from 0 at point 4 to B at point 5. Now clearly on the along the x-axis, when I write the equation of the equilibrium along the x-axis, I must obtain that the summation of the R along x-axis is equal to 0, because along the x-axis we have no shear flow. So if you see S1 is in direction from right to left, S2 is in direction from left to right. So S1 generate the shear flow on upper flange, generate a positive R12x, but on the lower flange we with the S4 from left to right, and for the orientation of shear flow generate an opposite reaction that is equal in value to R12x. So the sum of the R12x plus R45x is equal to 0 Newton. So the equilibrium along x-axis is satisfied. Now, along the y-axis, I must obtain that the summation of Sy plus R24y is equal to 0. So, such that Sy is equal minus R24y. For the nature of our shear flow here positive. So, if I integrate the quantity R23y and R34y, I must obtain the resultant 24 as sum of these two quantities, 23 and 34, or I can calculate one of these quantity, for instance R23y, and multiply it times 2, because 23 and 34 are symmetrical, are two sides symmetrical. So as you can see, I obtained the same value of the force, 7.5 Newton at times 10 at 4 power. So this quantity are equal. I can think to multiply this quantity times 2 to obtain the R24 along y. Now, because this quantity here, R24 is positive, Sy clearly, when I sum this quantity here, I obtain clearly Sy minus 1.5 times 10 at 5 power Newton. So, if in MathCAD I made this ratio for to understand you that the summation of these two resultants along y divided the absolute value of Sy is equal 0.999. That clearly said us that the summation of these two quantities is equal to the shear load. So the web absorbs all the shear load in this case. R24y must be in opposite direction of the shear flow to balance the same shear flow. So as R24y must to be in the opposite direction of the Sy to balance Sy, and in this case to avoid bending moment and twist of our section. So, but I can calculate this quantity here, the distance from the 2-4 web from the shear flow. But to obtain this quantity here, I must say that now this is a arm of R12x, because here I have R12x. The arm is A over 2. Clearly, the other R45x generate a poor moment with respect with the R12x. So this is also A over 2. But these two arrows, if you see, generate the same moment that is this. So I must pick one of these resultant with respect to symmetrical axis. Remember, with respect to symmetrical axis, because shear center is here. So we obtain that R12x have generated torque, in this case because it's with respect to the z-axis, generated torque that is positive. Remember the convention that we have used in the last videos. So positive and under clockwise, so R12x times A over 2. Now we must consider the R24 along y direction. This clearly quantity here with respect to the shear center here, this quantity here is R24y, generate also a anti-clockwise moment, that is a torque with respect to 0, that is positive. But in this case we have plus R24y times E. This sum of moment must be equal to 0 for the equilibrium with at the moment. So we can obtain E, that is equal to R12x times A over 2 divided by R minus R2 for Y. And so I obtain here R21x times A over 2 divided by Sy. In this case, I instead of the R2 for Y, I reported the value Sy that is negative. In this case, we have the same quantity here, that is 0.028 meter, that is about 28 millimeter. Okay, so minus 28 millimeter, this quantity here tell us that the shear center is located at an y equal to ycg, so at an x. So now the reference axis that I use is this for simplicity, y and x. This axis is y and x. So shear center is located at y, that is A over 2, that individuated the x sim axis, where the shear center S is located. Now the x coordinate of the shear center is on the left side of the web at the location of minus 28 millimeter. So we have proved that the shear center of this section, Chi section shape, is located out of the section. So at in this case at 28 millimeter out of the section on the left. So now we can obtain the same plot on MathCAD, but made in also as a single function. You can see here the linear part of S1, this is upper flange, the parabolic trend on the web, and the other linear equation, the linear trend, on the lower flange. So this is all for the shear flow on the so this is the clearly diagram that we see everybody on the books. So this explanation, I hope that is clear. Now we on the channel I have made also a other video where I calculated the shear flow of this quantity. Is in Italian, in Italian language, but I calculated the shear flow with another strategy. So avoid the integral. Now I calculated the shear flow of the same channel shape, Chi shape, with using the integral and the convenient chosen abscissa S1, S2, S3, S4. This is the method suggested by THG Megson, and I clearly is most powerful with respect to the strategy that used the calculated the moment, the first moment of area a part of the whole of the single rectangular shape and so on, as described in the past videos. This is quite simple. You now know as do this thing for this open section. This discussion is useful for all the open section. Also, if I have an I-shaped beam, so but with opportune choosing of the abscissa S. So the video can end here, and we will see at the next video. Bye.